Somewhere in the Pacific Ocean, right now, a patch of water the size of a continent is running a fever. Not a small one, not a normal one. Scientists who track this for a living are watching numbers they don't usually see outside of the strongest events ever recorded. They're calling it a possible super El Niño, and if it forms the way the early signs suggest, the effects won't stay in the ocean. They'll reach into your weather, your food prices, your electricity bill, storms forming on the other side of the planet from you. Because here's what almost nobody realizes: El Niño isn't a storm. It isn't a single event. It's a shift in the ocean's temperature that quietly rewires the entire planet's weather machine, thousands of kilometers away from where it starts. And right now, that machine is shifting gears. Stay with me. Because by the end of this, you'll understand why a patch of warm water in the middle of the Pacific can decide whether your winter is dry or drowning. To understand what's building in the Pacific right now, you have to understand what El Niño actually is. And most people don't. Not really. It's not a storm. It's not a hurricane season. It's something quieter and in some ways stranger. A shift in where heat sits inside the largest ocean on Earth. Normally, trade winds blow from east to west across the tropical Pacific, pushing warm surface water toward Asia and Australia. Behind that warm water, cold water rises up from the deep off the coast of South America. That's the ocean's default setting, the one it holds most of the time. But every few years, those winds weaken. Sometimes they stall, sometimes they even reverse. And when that happens, the warm water that was piled up in the west starts sliding back east, spreading out across the middle of the Pacific like something exhaling. That's El Niño, a redistribution of heat, thousands of kilometers wide, that quietly reprograms the atmosphere above it. And once the atmosphere reprograms itself over the Pacific, the effects don't stay there. They ripple outward through what scientists call teleconnections, long-distance links between weather in one part of the world and weather in another, connected not by chance, but by the physics of how heat and pressure move through our shared atmosphere. Here's where we are right now. As of this month, NOAA's Climate Prediction Center has placed the Pacific under an El Niño advisory. Their official assessment gives a greater than 90% chance that this event strengthens into what they classify as very strong during the fall and winter of 2026 into 2027. That number is worth sitting with. 90% isn't a maybe. It's about as close to certainty as climate forecasting gets. At NOAA's Geophysical Fluid Dynamics Laboratory, researchers running ensemble prediction models have been watching something else: consistency. Their August forecast shows dozens of independent model runs, each starting from slightly different conditions, converging on the same outcome: an El Niño that keeps intensifying through the fall, likely peaking sometime between October and January, at a strength that could rival the most powerful events ever recorded. Not one model guessing, dozens agreeing. To understand why that matters, you need a reference point. In the modern satellite record, only a handful of El Niño events have ever been classified as very strong. 1982 into 83, 1997 into 98. 2015 into 16. Each one reorganized weather patterns across entire continents. Each one is still studied, decades later, as a benchmark for what this phenomenon is capable of doing at its most extreme. If the current event follows the trajectory the models are showing, it would join that short, exclusive list. I want to be careful here, because this is exactly the kind of story that's easy to oversell. A forecast is not a guarantee. Even a 90% probability leaves room for the Pacific to surprise us. El Niño events have weakened unexpectedly before, stalling out short of predictions. Climate scientists who study ENSO are not claiming certainty about the future. They're describing probability, built from ocean temperature data, wind patterns, and decades of model validation. And right now, the probability is unusually high and unusually consistent. But here's what makes this event different from a routine El Niño year. It's not just that the Pacific is warming, it's how fast and how uniformly it's warming. Sea surface temperatures across the central and eastern tropical Pacific have been climbing since spring. And by the World Meteorological Organization's own May assessment, the shift toward El Niño conditions had already reached probabilities near 90% for the months ahead, months before NOAA's advisory even confirmed the event was fully underway. That's two independent institutions using different models, arriving at the same conclusion months apart. In climate science, that kind of agreement doesn't happen by accident. It happens when the signal in the ocean is loud enough that it's hard to miss, no matter which set of equations you're running it through. So what does very strong actually mean once you translate it out of the language of probabilities and ocean indices? It means a measurable, temporary boost to the entire planet's average temperature, somewhere in the range of 1 to 3/10 of a degree Celsius, layered on top of whatever long-term warming trend is already underway. It means storm tracks bending. It means some regions bracing for drought while others brace for flooding, often at the exact same time, thousands of kilometers apart, driven by the same event in the same ocean. It means, in other words, that a patch of unusually warm water most of us will never see is about to reach into places we will absolutely feel, starting with where the rain falls and where it doesn't. Let's make this concrete. Because shifting weather patterns is the kind of phrase that sounds important and means almost nothing until you can picture what it actually does to a specific place, on a specific continent, to people who have no idea the Pacific Ocean is the reason their year just changed. Start with Indonesia and stretch that same story across Australia and parts of southern Africa. During strong El Niño events, the rainfall that normally forms over the warm western Pacific follows the heat as it shifts east, which means the rain goes with it. Indonesia has faced severe drought conditions during past strong El Niño years, dry enough to fuel some of the largest peatland and forest fires on record, blanketing entire regions in smoke for weeks. Australia has faced its own version of the same story: reduced monsoon rainfall and drought stress across the country's agricultural regions in the strong El Niño years of the past. Now cross the entire ocean to the other side of the same event. Along the coast of Peru and Ecuador, the region that gave El Niño its name from fishermen who noticed unusually warm currents arriving around Christmas, the opposite happens. Warm water piling up off the coast fuels heavy rainfall and flooding. The 1997 into 98 event, one of the strongest ever recorded, brought catastrophic flooding to northern Peru, reshaping roads, homes, and river systems in ways that took years to recover from. Same event, same ocean, opposite outcomes on opposite sides of it. That's the part that's genuinely strange about El Niño. It doesn't create uniform disaster. It redistributes weather like cards being dealt from the same deck, some regions getting drought, others getting flood, all from a single shift thousands of kilometers offshore. Move north to the United States, and the pattern shifts again. Strong El Niño winters tend to push the Pacific storm track further south, which historically has meant wetter conditions across the southern tier of the country, California, the Gulf Coast, the Southeast, while the northern United States often runs milder and drier than average. The 1997 into 98. El Niño brought some of the wettest winter conditions California had seen in decades, along with damaging mudslides in areas stripped of vegetation by prior wildfires. Meteorologists at the time and in the years since have pointed to that event as a case study in how a single ocean pattern can turn a drought-stressed landscape into a flood risk almost overnight. None of this is guaranteed to repeat exactly. Every El Niño is shaped by its own particular combination of ocean temperatures, atmospheric conditions, and timing layered on top of a climate that has warmed measurably since the last comparable event. Researchers who study ENSO are careful to note that historical analogs, comparing to this event to 1997 or 2015, are useful for understanding tendencies, not for predicting exact outcomes region by region. But the tendencies themselves are well established, built from decades of observed data across dozens of past events, not guesswork. And what makes forecasters attentive to this particular event is the combination of two things at once: the strength the models are projecting, and the speed at which conditions have developed. Sea surface temperatures that were still ENSO neutral earlier this year have shifted quickly toward a very strong classification, a faster escalation than some past events followed. There's something worth pausing on here, beyond the mechanics. Every one of these regional stories, the smoke over Indonesia, the flooded roads in Peru, the mudslides in California, starts in the exact same place. A few degrees of extra warmth, sitting in surface water in the middle of an ocean most of the people affected will never sail across, let alone see. We tend to think of cause and effect as something that happens close together. A fire needs a spark right next to it. A flood needs a storm right overhead. But this is a different kind of causality, slow, oceanic, and enormous in scale. The spark is a temperature anomaly. The fire, metaphorically, shows up 8,000 kilometers away, months later, in a place that has no idea it's connected to anything happening in the Pacific at all. That disconnect, more than anything else, is why El Niño rarely gets the attention it deserves until it's already reshaping someone's year. It doesn't look like a single storm bearing down on a coastline. It looks like a slightly warmer patch of ocean on a satellite map, updated once a month, in a report most people will never open. And yet, if the current forecasts hold, this patch of ocean is on track to become one of the strongest instances of this pattern the modern instrumental record has ever measured. Not a routine seasonal shift, something closer to the outer edge of what this system is capable of doing. There's a number that tends to get lost in all of this. Not a percentage, not a probability, a temperature. The actual number the entire planet is measured against. Every year, climate agencies around the world calculate a global average temperature, and every so often, that number sets a new record. What most people don't realize is how often those record years line up with strong El Niño events. 2016, still one of the hottest years ever measured at the time, arrived on the back of one of the strongest El Niños on record. It wasn't a coincidence. El Niño acts like a short-term amplifier sitting on top of the planet's long-term warming trend, releasing heat that the ocean had been storing beneath its surface and handing it to the atmosphere all at once. Think of it less like a separate event and more like a booster shot layered onto a fever that was already running. The long-term trend is the fever. El Niño is what pushes the number, briefly, even higher than the trend alone would explain, which means if the current event peaks anywhere near the strength the models are projecting, the years it touches, 2026 into 2027, sit in a strong position to compete for the title of hottest year on record. Not because the underlying warming suddenly accelerated overnight, but because a temporary, powerful, oceanic mechanism just added its own weight on top of it. Climate scientists are careful with this distinction, and it's worth being careful with it too. El Niño doesn't cause long-term climate change. It's not the same mechanism, and conflating the two would be its own kind of error. But it does temporarily reveal, in a single number, what the planet's warming trend is capable of doing when it gets an extra push. A preview, briefly visible, of a version of normal that's still a few decades away for most other years. Now follow that same warmth somewhere less visible than a headline temperature record, into the economy that quietly runs underneath almost everything you buy. Strong El Niño events have historically disrupted agricultural production across some of the regions most affected by the shifting rainfall: palm oil and coffee production in Southeast Asia, wheat and grain harvests in parts of Australia and South Africa, and fisheries off the coast of South America, where warmer water pushes the cold, nutrient-rich currents that anchovy populations depend on further from the surface. The anchoveta fishery off Peru, one of the largest single-species fisheries on the planet, and a major global source of fish meal used in animal feed, has collapsed during past strong El Niño years, sometimes falling to a fraction of normal catch levels almost overnight. Follow that fish meal supply chain far enough, and it touches the cost of raising livestock on the other side of the world. Follow disrupted coffee and palm oil harvests far enough, and they touch supermarket shelves that have nothing to do with the Pacific Ocean, in countries that will never experience a single day of unusual weather from this event directly. That's the part that tends to surprise people the most. You don't need to live anywhere near the tropical Pacific to feel the economic edges of a strong El Niño. You just need to buy food, use electricity, or live somewhere that depends, even indirectly, on a global supply chain that quietly assumes the weather will behave the way it usually does. Insurance markets track this too. Reinsurance companies, the enormous financial institutions that insure the insurance companies covering floods, droughts, and storm damage, factor ENSO forecasts into their risk models months in advance because a strong El Niño reliably shifts where extreme weather claims are likely to cluster that year. It's a strange thought if you sit with it. Somewhere in a spreadsheet, in an office far from any ocean, a financial analyst has already adjusted a risk model because of what's happening right now in a patch of water most of us will never think about again after this video ends. None of this is speculative fear-mongering dressed up as science. It's the documented, historical pattern of what strong El Niño events have done before, described by the researchers, agricultural economists, and risk analysts who study exactly this kind of cascading system for a living. The uncertainty isn't whether a strong El Niño reshapes food, water, and money on a global scale. History says it does, reliably, almost every time. The uncertainty is only in the details: which regions, how severely, and exactly when the effects peak. What's different here isn't the mechanism, it's the odds. A greater than 90% chance of reaching very strong intensity means this isn't the mild, easily absorbed version of the story. It's closer to the addition that reshapes headlines, harvests, and household budgets on nearly every continent it touches. Let's go back to the water itself, because underneath every economic ripple and every shifted storm track, there's a more direct story. What this much warmth actually does to the life living inside the ocean where it starts. Coral reefs are, in a very real sense, thermometers with a nervous system. Corals survive in a narrow temperature range, in partnership with tiny algae living in their tissue that provide most of their color and much of their food through photosynthesis. When water gets too warm for too long, that partnership breaks down. The coral expels the algae, loses its color, and is left pale, stressed, and vulnerable. Scientists call this bleaching, and a bleached coral isn't dead yet, but it's starving, and if the heat doesn't ease in time, it will be. Strong El Niño events have historically triggered some of the most severe global coral bleaching episodes on record. The 1997 into 98 El Niño coincided with a mass bleaching event that affected reefs across dozens of countries simultaneously. The first time scientists had documented bleaching at that kind of global, synchronized scale. The 2015 into 16 El Niño triggered another one. part of what researchers later described as the longest global bleaching event ever recorded, stretching across 3 consecutive years. Reefs can recover from bleaching if conditions ease and the coral has enough time. But recovery isn't guaranteed, and it isn't fast. Some reef systems take a decade or more to rebuild what a single severe bleaching season stripped away, if they rebuild at all. And every additional bleaching event arrives on top of the baseline ocean that's already warmer than it was during the last one, layered onto reefs that in many regions are still recovering from the previous bleaching, from pollution, from overfishing. Researchers who track global reef health describe this less as a single crisis and more as a compounding one, where the recovery windows between disturbances keep getting shorter. It's worth pausing on why this matters beyond the reefs themselves. Coral reefs cover a small fraction of the ocean floor, but they support a disproportionate share of marine life. Juvenile fish nurseries, food webs that stretch out into open water, coastlines that reefs help protect from wave damage. When a reef system is stressed at this scale, the consequences don't stay contained to the reef. They move outward, the same way the economic effects of El Niño moved outward from a fishery collapse into a global supply chain. There's a specific kind of marine heatwave scientists have started tracking more closely in recent years. Not just the broad Pacific warming that defines El Niño itself, but localized patches of extreme ocean heat that can form on top of it, sometimes called compound events. These localized hotspots can push local temperatures well above what the broader El Niño pattern alone would predict, hitting specific reef systems, kelp forests, or fisheries especially hard, almost like a heat wave inside a heat wave. None of this happens in isolation from everything we've already talked about. The same warm water reorganizing rainfall over Indonesia and Peru is the water bleaching reefs in the same ocean basin. The same event nudging global temperature records upward is stressing marine ecosystems that have no capacity to simply wait out a bad year, the way a delayed harvest might recover the following season. A reef doesn't get a second chance the way a wheat field does. What's lost during a severe bleaching event can take a generation, in ecological terms, to come back, if it comes back at all. I think this is the part of the story that's easiest to lose entirely, underneath the discussion of forecasts and probabilities and percentages. Somewhere beneath the surface of that warm patch of Pacific water, in real time, coral colonies that have been growing for decades, sometimes centuries, are experiencing conditions that could unmake them within a single season. Not one dramatic event, just heat, sustained too long, in water that used to run cooler. Scientists monitoring reef systems this year track heat stress indices, the same way meteorologists track a hurricane's projected path. Accumulated thermal stress, week by week, region by region, trying to anticipate which reefs are heading towards bleaching the thresholds before it happens. A strange kind of forecasting, watching a slow-motion event unfold somewhere most of us will never dive into, guided by satellite data rather than anything visible from the surface. That's the through line connecting everything in this story so far. The reefs, the fisheries, the storm tracks, the temperature records. None of it announces itself the way a hurricane does, with a name and a projected landfall. It arrives as data, quietly accumulating in places most of us will never look until the consequences show up somewhere we can no longer ignore. Here's something that changes the shape of this story once you sit with it. We've never gone into an event like this one as prepared as we are right now. The 1997 into 98 El Niño, one of the strongest on record, caught much of the world by surprise. ENSO forecasting was still a relatively young science at the time, and many of the regions hit hardest by flooding, drought, and disease outbreaks had little warning to prepare. The World Health Organization has documented how that event contributed to outbreaks of cholera and other waterborne diseases in flood-affected regions, and to malaria surges in areas where shifted rainfall created new breeding grounds for mosquitoes. Researchers who study the human toll of that event have estimated it caused tens of thousands of deaths worldwide through a combination of flooding, drought, famine, and disease. Though exact figures vary across different studies and remain difficult to calculate with certainty, that was nearly 3 decades ago. Since then, forecasting has changed dramatically. Agencies like NOAA and the World Meteorological Organization now issue monthly ENSO updates months in advance, tracking ocean temperatures, wind patterns, and model consensus with a level of detail that simply didn't exist in the late 1990s. Countries that were blindsided in 1997 have spent the years since building early warning systems, adjusting agricultural planning, and pre-positioning flood and drought response resources specifically around ENSO forecasts. None of that makes a very strong El Niño harmless. It doesn't undo the physics of what a shift this large does to global rainfall. But it does mean that, this time, almost nobody working in climate science, agriculture, or disaster response is being caught off guard. The warning arrived months ago. What happens next depends largely on how seriously that warning gets used. I keep thinking about that gap between a warning and an outcome. We have the data now. We've had it for months. The question this event is quietly asking every government, every farmer, every insurance analyst, every fishing community watching their coastline is whether having the warning actually changes what happens when the warm water arrives. That's also, in a strange way, the same question underneath everything this channel exists to do. Not just to tell you that something is happening in the world, but to give you enough of the actual mechanism behind it that you're not just reacting to a headline. You're understanding the thing the headline is describing. If that's useful to you, if you'd rather understand the machinery of the world than just scroll past another alarming number, that's exactly what we do here, every day. Subscribing costs you nothing, and it tells us there are more people out there who want the deeper version of these stories, not just the panic-inducing version. Because here's the honest complication in this particular story. A strong El Niño isn't purely a disaster, and it isn't purely neutral either. It brings life-saving rain to drought-stressed regions of South America, even as it brings drought to Southeast Asia. It can end multi-year dry spells in parts of the southern United States, even as it stresses coral reefs on the other side of the planet. There isn't a single moral to this event, the way there is with a wildfire or a single storm. It's a redistribution, and redistribution always means someone receives what someone else loses. That complexity is exactly why the forecasting matters so much. A community that knows a strong El Niño is coming can plant different crops, reinforce flood defenses, or adjust water storage months ahead of time. A community caught by surprise absorbs the same physical event as a crisis instead of as a planned-for season. The ocean doesn't care either way. But the outcome for the people living through it depends enormously on whether the warning reached them in time and whether anyone acted on it. We are, right now, living inside that window. The forecast has been issued. The probability sits above 90%. What happens across the months ahead isn't really a mystery of physics anymore. The ocean has already shown its hand. What's still unwritten is how well the rest of us respond to what it's telling us. There's a version of this story where the warning gets used well, where the reservoirs in drought-prone regions fill ahead of schedule instead of scrambling afterward, where farmers plant flood-resistant varieties instead of losing a season, where coastal communities move fishing operations before a collapse instead of after one. And there's a version where the warning sits in a report nobody outside a handful of agencies ever reads, and the world simply waits to find out what happens, the way it always used to. Both versions are still possible. The difference between them isn't the ocean, it's us. There's one more piece of this that researchers are already thinking about, even before this event peaks. What happens after? El Niño doesn't just end quietly and leave the Pacific back where it started. Strong events often set up their own reversal. The same heat that gets released into the atmosphere during El Niño eventually leaves the ocean's surface layer depleted, and Pacific systems have a well-documented tendency to swing the other direction once a strong El Niño fades, tipping into La Niña, its cooler counterpart, sometimes within a year or two of the peak. Forecasters at NOAA and other agencies are already watching for early signs of that potential swing in their longer-range outlooks, the same way that they'd watch a pendulum that's about to reach the top of its arc. If that pattern holds here, it means the world isn't just bracing for one climate shift, it's bracing for two, back to back, a very strong warm phase, potentially followed within a couple of years by its cooling opposite, each one rearranging rainfall and temperature patterns in its own distinct way, in some cases across the exact same regions that just adjusted to the first shift. I find something almost dizzying about that. We tend to think of returning to normal as the natural endpoint of a disruption. The storm passes, the water recedes, things go back to how they were. But the ocean doesn't really have a normal to return to. It has a range it oscillates within, warm phase to cool phase and back again, on a rhythm that's irregular enough that nobody can predict it more than a year or two out with real confidence. What we call normal is really just the average of a system that's constantly swinging between extremes we experience one at a time. That's worth remembering the next time a strong El Niño or La Niña makes headlines as though it's a singular, isolated event. It isn't. It's one visible swing of a pendulum that's been moving for as long as the Pacific Ocean has existed, largely unnoticed for most of human history, simply because nobody had the instruments to watch it happen in real time. We do now. And that's really the strange privilege sitting underneath everything in this story. Not that the ocean is doing something unprecedented. Oscillations like this predate written history by a wide margin, showing up in coral growth records and ice cores stretching back centuries before anyone was measuring sea surface temperature with a satellite. What's unprecedented is that, for the first time, there's a species capable of watching the whole cycle unfold, modeling its trajectory months in advance and asking, in real time, what to do about what it's showing us. Scientists studying ENSO often describe it not as a problem to be solved, but as a rhythm to be understood and planned around, closer to the tides than to a disaster. You don't stop the tide. You build your calendar, your infrastructure, your expectations around knowing when it's coming. The unusual thing about this particular swing of the Pacific's rhythm isn't that it's happening. It's that the swing itself is unusually large, unusually well forecast, and unusually well understood, all at the same time in a way no previous generation watching this same ocean ever had access to. So the honest answer to what happens next isn't a single prediction, it's a layered one. In the coming months, a very strong El Niño, most likely peaking sometime this winter. In the 1 or 2 years after that, a real chance of swinging the other direction entirely. And underneath both of those, the same slow, patient rhythm the Pacific has been running for longer than there's been anyone alive to name it. There's something worth sitting with in that layered answer, beyond the forecasting itself. We tend to want a clean ending to stories like this, a single number that tells us whether the outcome was good or bad, a moment where the event is officially over. But the Pacific doesn't offer that kind of closure. It offers a continuous signal, rising and falling, that researchers will still be reading, adjusting, and reforecasting long after this particular El Niño stops making headlines. That's probably the most honest thing to say about where this story goes from here. Not that it ends, but that it keeps being written in monthly reports most of us will never open, by people whose job is to keep watching an ocean that never actually stops moving, on behalf of a species that's only just learned how to read what it's saying. So here's where this leaves us. A patch of ocean, warming faster and more uniformly than almost any comparable event in the modern record. A greater than 90% chance, according to the agencies that track this for a living, that it becomes one of the strongest El Niños humanity has ever measured. Rain, shifting away from some coastlines and crashing into others. Reefs absorbing heat that they've never had to withstand this early in a season. A global temperature record that may not survive the year. And underneath all of it, an ocean simply doing what it's always done, moving heat around a planet that was never built to hold still. None of this is new, in the deepest sense. The Pacific has been swinging between these two states for longer than there's been anyone alive to notice. What's new is only that we're watching, that the data reached us in time, that somewhere right now a farmer is choosing a different crop because of a forecast issued months in advance. A city is checking its flood defenses. A fishing community is watching a satellite map instead of just the horizon. You'll go about your week after this. The sky above you will look exactly the way it always does. Your coffee, your commute, your ordinary Tuesday, none of it will announce that anything has changed. But somewhere in the middle of the Pacific, an ocean is quietly rewriting the next several months for people it will never meet, in places it will never announce itself to directly. And in a few months, some of that rewriting may reach you too. In a grocery bill, a strange winter, a headline you finally understand instead of scroll past. That's not nothing. If this helped you understand something you didn't before, share it with someone who still thinks weather is just weather. And if you want more of these, the quiet mechanisms running underneath the headlines, subscribe. We do this every day. Before you go, tell me in the comments, has your part of the world already started feeling this? Wetter, drier, stranger than usual? I read everyone. I'll see you in the next one.